Hello everyone. Today we will continue talking about chapter 5 in your book, and we will try to solve some example problems. Let me start. Okay. What did we do on Monday? We introduced friction, circular motion, and we used Newton's laws. We explained that there were like two kinds of friction: kinetic friction, static friction. We introduced circular motion, and we said acceleration in circular motion is this, v squared over r, and speed is always tangential and constant. We introduced the dynamics of uniform circular motion, and we said the centripetal force is mv squared over r. And we showed the applications of this circular motion in highway curves, and we said generally friction provides this necessary centripetal force for highway curves, but in some cases you can do this kind of banked highway not to rely on friction. And we talk about non-uniform circular motion, and we said tangential and radial components can be decomposed and studied separately, pretty much the same way we decompose vectors in ijk coordinates in earlier weeks. Okay, I think these are the problems. I think this one we solved. This one we solved. If you guys have any questions about these problems, we can go through that. And now I want to solve these two problems. Okay, just two more problems. This will make all of the recommended problems of this chapter solved, and you can go through it later. So let's start with this problem. Let me zoom a little bit. An object of mass m is constrained to move in a circle of radius r if its tangential acceleration as a function of time is given by this. A tangential is equal to b plus ct squared with b and c constants. And if v is equal to v naught at t is equal to 0, determine the tangential and radial components of force F10 and Fr acting on the object at any time t bigger than 0. Okay, I will give you, let's see, 2 or 3 minutes. Okay, so what do you guys think about this problem? So any ideas? Let me hear a couple of suggestions and then I can start. What do you think we should do? Okay, F is equal to MA, so F10 is equal to B plus CT squared. Okay, I got an answer. Any other answers? How do I start? Maybe I can start with drawing a picture and looking at it. So let me start with, so this is a circular motion. Let's draw a circle, okay? And it says it starts with this guy, right? Let's put this guy, I think we can put it anywhere, but I'll put it like something here. Okay, and this is V is equal to V naught. And that's not the only thing, right? There is also like some tangential acceleration. Let's also put, I'll shift this a little bit so that they don't overlap, but you understand that. So this is a tangential, okay? So that's what I understand from tangential, right? There's like a tangent means like a tangent, and tangential acceleration means like this. And these are at t is equal to 0. And this is asking, determine the tangential and radial components of force. So this is a circular motion. And in circular motion, I know, so I need this radial acceleration, right? The radial acceleration, I know this is like a circular motion. A radial is v squared over, what is the radius? Is it given? Okay, r, okay? At any point. So I need to find v, this, and v here is always tangential. Why? Because this is circular motion. If it was not, it would not be a circular motion. Okay. Now, basically, this is like a decomposing. Okay, let's put that guy in here. I don't like that. Okay. Okay. Let's call this AR. So I just decomposed it in two vector components. And velocity has only one component. Velocity doesn't have such a component, otherwise it would go off the circle. So what do I do? Now I need to calculate V at a bigger time, right? Let me do this. So V is equal to V naught at T is equal to 0. So then V is equal to V naught plus A times T, right? And I write this as V naught plus B plus C T squared times T, which is equal to V naught plus BT plus CTQ. Simple. Any objections? Right? That's what you get, right? So I want to check this. Like, how can I check this? I want to make sure I got the right result. What can I do? This one? What's wrong with this? What do I know about velocity? What can you do with velocity? Derive it with respect to t. Okay, so if you say that dv dt, then what is this? Let's look if we had this, like let's look at our notes. Okay, this is an example. This is another example. Okay, here is this section I need to look, right? This is like a non-uniform circular motion. There's like tangential and radial forces, good tangential radial accelerations. And I decompose force and acceleration in its components, tangential radial. And here's what it is. A tangential is dv dt, a radial is v square over. And A total is this. Let me use this. Okay. This should be equal to A tangential. And let's do term by term. This first term is 0 because it's constant. If you take the derivative constant, it's 0. The second term, bt derivative is b, plus this last term is like take this 3 to here, decrease the power by 1. 3 times c times t squared. Now I need to check this with what was given. What was given was this guy, right? A10 was b. Now I have a problem. How do I reconcile these two things? They don't make sense, right? So this one has t, c, t squared. This one has 3 c, t squareds. How do I fix this? It's 1/3, right? Where do I put 1/3? I just need to put a 1/3. And here, maybe I can use a red color. If I had initially 1/3 here, I would have 1/3 here. This 3 would cancel with this 3, and I would be in good shape. Now this is b plus ct squared, and this is b plus ct squared, and that just checks, okay? So you don't need to know some like integral, blah, blah. If you just look at things and then do things your way, you can get the right result. Now, do we guys all agree? Any problems here? Okay, this was the first step, right? Now we have V at any given moment. And from radial acceleration, I know what here, if you look at this result, when we derive this result assumes, okay, like I think it says constant acceleration. Okay, you can go ahead and look at that. And the assumption was A was constant. If A was constant, you would be able to do this. And here I look at A and I see that I actually messed up. I actually messed up because A was not constant and I used this guy. So I shouldn't be using this. But I told myself, okay, I happen to use it. And I don't want to go ahead and read the entire calculus book and learn about integrals. Who knows how long that would take. I just want to fix this. I just want to have the right result. And I think anybody can put 1/3 here, right? So I don't have to know the integral to fix it. Of course, the correct way is V should be some V naught plus integral dt A of t, 0 to t. But I don't want to talk about this because you don't need this. You don't need it for this problem. You don't need this for any other problems, at least this semester. So when you see something like this, I think that's why I wanted to pull this problem. You know, don't panic and try to fix it your way. Nobody can force you integral. Okay. Now, okay, a radial is v squared over r, and I just plug in v, right? V is tangential at any moment, so it's basically v naught plus bt plus 1/3 ct cube square divided by r. Now I can just use Newton's law. F is equal to ma, right? F tangent is equal to m times a tangent, which is equal to m times a tangent is already given, b plus ct squared. F radial is equal to m a radial, which is equal to m times v naught plus bt plus 1/3 ct cube squared over r. And that's it. I wouldn't say this is like a deep problem. I think it has some good message. You should relax and you should look at the problems with open mind, in my opinion. That's the message of this problem. So let's do one more problem. I think this is also fun. And then I can spend a few minutes to answer questions and then we can go. Everything we edit was edit for a reason. And I wasn't like, oh, this is like result. I don't like this result. Let me add 1/30. I didn't do this. I thought about this. I tried to like use my intuition. I tried to think and I found the right result. You don't add nothing arbitrarily. I think that's completely opposite of what we did here, okay? Let's think about this problem just a little bit. A small bead of mass m is constrained to slide without friction inside a circular vertical hoop of radius r, which rotates about vertical axis. So this hoop rotates like this, and this bead is constrained to move up and down here like this. It cannot just fall off or trip up. It's supposed to stay there, okay? As this hoop, of course, rotates, this speed, if you look at its trajectory, it's going to be something like that, right? Or maybe I can use that dot. So if you just look at this bead, ignoring the hoop, it's going to be something like that. And this is kind of like a circular motion. This is not kind of like a circular motion. This is a circular motion. So the problem is asking us to determine the angle theta where the bead will be in equilibrium. That is, it's going to stay where it is with respect to the hoop. Okay, it doesn't have a tendency to move up or down along the hoop. And they ask us to find this for F is equal to 2 revolutions per second and R is equal to 22 centimeters. Okay, we want to find theta. Okay, let me give you just 1 minute. Maybe you can start speculating. Any suggestions? Start with free body diagram. Good. This is mg, right? And the problem is telling that this is in equilibrium, but this means it will have no tendency to move up or down, right? So it should not move like this or like this. There should be something balancing this. And what is balancing is, since this hoop and this ball are in contact, right? They are in contact. There should be a normal force. And the normal force on the bead by the hoop is this guy. I think this is also clear, so maybe I just write it. Let me call this F normal. Now, F normal has two components. Okay, let's call them F normal X and F normal, sorry, this is X. I mess up X and Y, what's happening? So these are the components. Let me make it look a little pretty. This is Y. Okay, that one is good. Okay. So you said start with free body diagram, and I started with free body diagram. And then what? What do we do? Do I know this F normal? What is F normal? Right? I need to, okay, you guys are writing about F normal, so I'm assuming I need to find F normal. And what I know is like there's no motion along this direction. So because this guy is not going up or not penetrating through the hoop, so these two forces should cancel. Let's start with this guy. So F normal Y should be equal to mg. This is, by the way, saying that along Fy, m times a, and along Fy, and this one is 0. This comes from here, okay? But I'm just skipping these intermediate steps because I feel like you guys already know this. And F normal Y is equal to F normal times, and if this theta, if this angle is theta, this guy is theta, and this guy is cos side is cosine. So this is cosine theta should be equal to mg. Now I have what F normal is. Mg divided by cosine theta. Okay. Now let's look at the other component. F normal X is the only force along X, should be equal to m times A, but I know m times A is m times V squared over R. Now this guy is F normal times the opposite side sine theta, but I just found what this guy is, right? If you plug in, this is equal to mg sine theta over cosine theta should be equal to m V squared over R. So let's drop these m's. So we have to write less. Okay, so let me go back to problem. And the problem is asking determine the angle where the bead will be in equilibrium. And we need to find theta in terms of a given frequency, right? So here G is known, this is tangent known, R is known, so V is not known. So I need to express V in terms of frequency. And for that, that's right. V is delta X, delta T, okay? And total, okay, I can look at this. This guy starts here, makes a full circle, comes back. And I know this necessary time is called period, right? So this T, I want to put period. And the total distance in this necessary time, like this, is, we know, it's like 2 pi, like circle's radius. And circle's radius is r times sine theta in this case. This is 2 pi r sine theta. Okay, I don't want red color here. Let me fix that. Color black, okay. And so I can plug this in here. Okay, like maybe I can write one more thing because they are talking about frequency. And I know 1 over t, the period is equal to frequency, right? So I write this as like 2 pi maybe r f sine theta. Okay, now I can put this guy in here. So g times sine theta over cosine theta is equal to 4 pi squared r squared f squared sine theta squared divided by, okay, now I see one more thing I messed up. So this r here is the radius of motion, not the radius of the hoop, right? So I need to fix that too. So this is sine theta, this is sine theta, and this is r sine theta. Let's clean up these sine thetas. 1 sine theta here, 1 sine theta here, and 2 sine thetas here. And this gives gr over, oh, okay, I can cancel this guy too, which is rather nice. So there's, okay, so this is g over 4 pi squared r f squared, right, is equal to cosine theta. So let me check if I have everything. So I have g, okay, g is here, 4 is here, pi squared is, r is here, f squared is here. Good, I have everything. And I just basically use theta is equal to cosine inverse g over 4 pi squared r f squared. Okay, that's it. Maybe let me calculate for the givens. Let me calculate this guy. So g is 9.8 divided by 4 divided by pi divided by pi for pi squared. R is 0.22 divided by 0.22, and f squared is 2 squared is 4 divided by 4. This, now I'm going to take inverse cosine of all of this. Inverse cosine. Okay, I found 73.6 degrees. Theta is equal to 73.6 degrees. That's what I found. Okay, let's finish with this. Can the bead rise as high as the center of the circle? Which means this theta is equal to 90 degrees, so it's completely horizontal. Can this happen, and explain? What would you say? Can I go all the way to here? No, right? Why? Because then there is no normal force. Exactly. So if you were here, so gravity would pull you down. But we saw here it was like gravity, like that was giving normal force. Now there is no reason to have a normal force. So if there is no normal force, there is no circular motion. And we can actually see this mathematically here. If you look at that guy, so say theta is equal to 90 degrees. For that to happen, this should be 0, right? Or the other way of saying that is like cosine of 90 is equal to 0. So this should be 0, but this could not be 0, right? So G, R, these are like non-zero constants. You can increase F to make this guy smaller and smaller and smaller, but you have to reach an infinite frequency to make this zero. So you can spin this hoop as fast as you want, but it will never be 90 degrees because F will always be finite. Okay, that's it for today. For part C, is there a tension for normal force? Okay, good. So for part C, there is no tension, right? We write, okay, these are fictional lines. These are not physical. So don't think that there is like a string tying this. The bead is staying there by itself. So there's nothing connecting here. This here entire hoop is actually empty, right? If you like, the real problem is something, okay, I can use this. The real problem is there's like a hoop, okay? And this hoop is like this, and this guy is turning around its axis, and there's like a bead, and there's nothing connecting it to there. This is the real problem. There's no tension, okay? Oh, okay. Okay, guys, take care. I'll see you guys later, okay?